Hello everybody, my name is Chris Brady, author of the Boeing 737 Tech Guide and the Boeing 737 Tech Site, and this video is about the 737's PSEU. So those of you that follow my videos are probably thinking, I remember he's already done one of those. You're absolutely right. This video is a re-release of the one I did last October, and significant updates to this are I've now included the history and development of the PSEU right back from the original 737-100 and onwards. Got more details about the SPSEU in here because there was a little bit of confusion on that. Some more about switches and sensors, thanks to some feedback from a viewer, and more on the air-ground systems. So, contents of this, the background, PSEU, SPSEU, differences on the MAX, then a little section on proximity sensors, then we'll look in depth at the systems that the PSEU serves, crew procedures and problems and updates. As always, please treat your company training and their manuals as the authoritative source of information. Okay, so to kick off, what is the PSEU? Full name, the Proximity Switch Electronic Unit. It's a system on the NG and the MAX that communicates the position or state of system components, such as the gear, the doors, speed brake lever, etc., onto other systems. And it directly controls the following systems: so air-ground relays and discrete signals, the landing gear transfer unit, or transfer valve as the engineers call it, landing gear position indicating and warning, takeoff and landing config warnings, the speed brake deployed indication and warning, but not on the MAX, Airstairs control and warning, and door warnings. So, by way of an overview, just to kind of condense down what I've said there, so the inputs to the PSEU are the following sort of sensors and switches: the weight on wheels, gear up locks, gear down locks, speed brake lever, again that's not on the MAX but I'll come on to that, doors and air stairs. The systems controlled by the SPSEU are air-ground relays and discretes, air stair control, door warnings, overwing exit flight locks, landing gear transfer unit, gear indicators, speed brake warning, takeoff and landing config warnings, the tailskid, which is an SPSEU function, and the mid-exit doors, which are also SPSEU. Alright, let's have a look at the background. So, whilst the PSEU is only installed on the NG and the MAX, its origins actually go back to the very first 737s ever produced, where it was known as the landing gear electrical module. I don't unfortunately have a photo of the original unit, but it's very, very similar to this one, which replaced it soon after, which is known as the landing gear accessory unit. The only difference, and I can only go by drawings I've seen of it, where the ground and air sensing test lights and buttons that you see there at the top left of this unit were actually in a sort of figure 4 shape across the top of the box, much like that anti-skid auto brake control unit just to this box is right actually. Anyway, so as you can see, it was an LRU, a line replaceable unit in the E&E bay. Its purpose was to process the state of the landing gear proximity sensors. From that, it could decide whether the aircraft was in the air or on the ground. That was then passed on to other aircraft systems, and the exhaustive list as of the originals, so these are 737-1 and 200s, was just landing gear lever lock, anti-skid, APU fire warning, thrust reverser, hydraulic interconnect valve, static inverter, drain mast heater, store warner, flight recorder, aircon turbofans, takeoff warning, cabin pressurization control, voice recorder, wing anti-ice, electrical systems, main cargo door control for those that had it fitted, flap load limiter, and auto brakes. Now that might seem as quite a long list, but trust me, on the current generations of 737s, it's a whole lot longer, and I'll show you the full list later on in this video. This photo, by the way, big shout out to the Moorabbin Air Museum in Melbourne for providing this photo. But obviously, these days I don't have access to any 737-200s anymore. Okay, so for the that landing gear accessory unit that you just seen on the previous slide, that was replaced by the landing gear logic shelf, and this was actually in place on some of the later model, the very later model 200s, but it was mostly the classics. So the classics all had this. Now, this was taken out of the E&E bay and put here in the forward equipment compartment. And that is actually where the PSEU on both the NG and the MAX remain today. So that's where it is. This close-up of it shows you that basically this is the front of it, but behind it what you've got is a box, and that contains up to 18 printed circuit cards, relays and test switches for systems affected by landing gear logic. This is one of the later ones, so it's got the full 18 on there, but other earlier iterations of this had less relays, less fail indicator lights and what have you. So this was the latest, most comprehensive of the E11 rack. So onto the PSEU. That's it in its present location. Again, it's in the forward electronic bay. So it replaces the landing gear logic shelf. So the NG and the MAX don't have that. They've just got this. It does away with all the printed circuit cards, and perhaps more importantly, it extends the functionality of the system beyond the landing gear. So the PSEU, it controls the following. As you already said, air ground relays, landing gear transfer unit, landing gear position indicating warning, takeoff and landing config warnings. But in addition to what the PSEU now does, that the previous system on the classics and the originals didn't, it also handles the Speedbrake deployed indication and warning, although not on the MAX. The Airstairs control and warning, and the door warnings. So those features are the ones which are new for the PSEU. So looking at the actual unit itself in a bit more detail there, I say it's in the same place as the landing gear logic shelf, so that's why it's in the forward equipment compartment. You got 7 large connectors on the left, each one of which is a kind of wiring loom in itself, and their inputs from the various sensors and outputs to the 2 air ground systems. There's also a bite panel on the front for sort of error checking, fault finding, and a large decal up there on the toward the top, which has got basic instructions for use and also instructions for sensor rigging. Taking a closer look at the bite panel, this can actually show over 300 different fault messages for the engineers. Each message can either be showed as an ATA reference that you can see on the left there. So 32 is ATA 32 is anything to do with the landing gear, or in a plain English version. So that's it on the right, which is right on ground A fault. Just to help out the engineers who haven't memorised their fault isolation manual, as I'm sure most of them have. The faults are either listed as current faults, or they're put into fault history if the condition disappears, which is more common than you'd think. And the bite panel can also be used by engineers to put the aircraft into the air state for testing. More on that later. Now, because the PSEU is so important to the correct functioning of so many other systems. I mean, its reach goes far and wide throughout the aircraft. It's got both a primary and an alternate power source, and that alternate power source, if you look at it, is the hot battery bus. So if you're down to just battery power, then Boeing has deemed the PSEU to be so important they want to keep that alive for you. The circuit breakers for the PSEU are on the P63 panel in the miscellaneous column on the left, because of course it's an add-on, only came in with the NG. What kind of preceded it, I guess, were those pair of circuit breakers on the right there, which are the air-ground systems. They're on the other side of the same panel under landing gear. Now, the PSEU is just a component of the air-ground system, but it is by far and away the most important component, the main component. It's the heart of the air-ground system. You wouldn't have an air-ground system without the PSEU. But it isn't quite true to say that the PSEU is the air-ground system. But again, I'll come on and talk about the air-ground systems later on, which will hopefully shed a bit more light on this. Talking of lights, all NGs have a PSEU and all NGs have a PSEU light on the aft overhead panel. That light's inhibited on the takeoff roll from when the thrust lever angle is beyond 53 degrees and in flight until 30 seconds after landing. So basically it'll only come on the ground. Right, the SPSEU. What is it? It's well, the name, it's a supplemental or supplementary PSEU. It's one or two electronic cards used on some NGs. It's located in the J23 junction box in the E&E bay, and it controls the following systems. A two-position tailskid, if installed, so that would be the 800 SFP and the 900 ER, and mid-exit door flight locks, if activated, and they're on just the 900 ER. The Max doesn't have an SPSEU. It all got integrated into the Max versions of the PSEU. So that right there, that's the SPSEU. It's just one or two electronic cards. The SPSEU has got a separate card for each of its two functions, so mid-exit door flight locks and or the two-position tailskid as fitted to the individual aircraft. Now the card in slot A, that always controls the two-position tailskid. That's your upper photo. The card in slot C, which is shown in the lower photo, controls the mid-exit door locks, and again it's only fitted to the 737-900ER, which have got the mid-exit doors activated. If the doors are deactivated, which is again perhaps more common than you'd think, that card is removed. Slots B and D are not used for SPSEU functions as far as I know. I would imagine if they are used for anything, it will probably be for things on the military versions of the 737. But I don't know. I genuinely don't know. Now the SPSEU light, again, I think this is probably where the confusion comes into, does my aircraft have an SPSEU or not? This is probably where it arises from. So only 737-900ERs have got the SPSEU light. All NGs with a two-position tailskid have got an SPSEU card, but not necessarily a light. The two-position tailskid has got no output to the SPSEU light, so the light isn't fitted unless, of course, the aircraft's got mid-exit doors. So all 737-900ERs have got the SPSEU light fitted. However, if the mid-exit doors are deactivated, the light will be placarded in up by maintenance. There we go. So again, I hope I'm clarifying and not muddying the waters, but I've put photos down there of your three combinations. So the top one, the SPSEU light and the PSEU light, that will only ever be there on the 737-900ER with active mid-exit doors. If the doors are deactivated, engineering will have put an in-op sticker on it. All other 737 NGs except for the 900ER have only got the PSEU light because they don't have mid-exit doors. So, if I could try and summarise, how do you know whether you got an SPSEU light or not? I mean, I guess my point of the previous slide is to just say the presence or lack of an SPSEU light is not the way to tell if you got an SPSEU fitted. And the reason there is because the 800 SFP has got an SPSEU, and you can see it there because I took this photo from an 800 SFP, but it doesn't have an SPSEU light. If you've got either a two-position tailskid or functioning mid-exit doors, then you've got an SPSEU. That's really the bottom line. And you can confirm this if you really want to by opening the J23 box to see if any SPSEU cards are present. There you go. Hope that's cleared it up. Alright, max differences. On the Max, the PSEU and the SPSEU are combined into one unit, which is still called the PSEU, and it's still in the forward equipment bay. This includes all of the functions of the PSEU and the SPSEU of the NG. I guess the most obvious difference is it just looks completely different. You know, it's a rectangular box with 7 big wiring looms, just as the PSEU was, but there's no decal on it, and there's no bite panel on it. There's no bite panel on it because any current faults and fault history are now read from the OMS pages in the flight deck, and there's no decal on there because there's no reason to go in there and make any adjustments using that bite panel, because again it's all done from the OMS pages. So so there you go. So it looks quite different, but actually it's the same thing. It just integrates the SPSEU as well. So other differences apart from how it looks are well, the two main ones are these. The Max gear lever, as you know, doesn't have an off position, and that's because the function of the off position to remove hydraulic pressure was taken over by the PSEU. So the Max PSEU will remove hydraulic pressure from landing gear 10 seconds after all gear are up and locked. And this in turn was just basically to save space in the on that panel, so you could fit the large displays on. The second big difference was that the Speedbrake's extended warning light, which is controlled by the PSEU on the NG, that's now controlled by the spoiler control electronics unit on the Max. The logic's exactly the same, but since the Speedbrake lever position is ascertained by the SCE on the Max, the logic and the output driver for the light is contained within the SCE rather than the PSEU. So there we go. I mean, subtle difference, absolutely transparent to us as crew. All the functionality is exactly the same. It's just that it now comes from the spoiler control electronics unit rather than the PSEU. The maintenance light. So the previously perhaps confusing SPSEU and PSEU lights of the NG are now replaced by a single maintenance light on the Max, and that is, before I get the question, that's even those Max models with mid-exit doors. So your 8200s, your Dash 9, your Dash 10 or whatever, they've all only got the one maintenance light. Now, the maintenance light also indicates other non-PSEU status level faults, which kind of things which must be checked by engineers before dispatch using the maintenance control page of the onboard maintenance system. Hard faults will usually bring on the associated system caption, for instance spoilers on the flight controls panel. Status level faults will only bring on the maintenance light. The The maintenance light, like the PSEU light, it's inhibited in flight and during engine start. So these are the maintenance data pages on the Macs, and they can show the current position of the air ground system, landing gear, lever and doors, and the proximity switch gaps and tolerance ranges. It also shows the takeoff config inputs and states, for instance the Speedbrake from the spoiler control electronics unit, and the flaps from the FSEU, and the landing gear transfer unit as well. They're all shown on these maintenance data pages for the Macs. The onboard maintenance pages, which is just sort of 2 clicks over to the top right there from the maintenance data pages, these allow engineers to set the air ground system 1 and or 2 in the air. And again, please let me say, do this with extreme caution, because a lot of unexpected things happen when you tell an aircraft it's in flight when it's on the ground. You can also reset emergency exit latches and extend the 2-position tailskid for maintenance. That tailskid extension function that replaces the switch that was on the outside of the J23 box, which coincidentally is the one that contains the SPSEU cards in the ENIB bay on the NG. So that switch has gone on the Macs because it's all done from these onboard maintenance pages. Right, proximity sensors. I've included this following some really good feedback from a viewer of my first PSEU video, who it was quite rightly getting annoyed with me because I was using the word switch and sensor interchangeably, and they're not, and he was absolutely right to point this out. I must admit, I tend to call proximity switch. I tend to call proximity sensors proximity switches. Strictly speaking, they're not, and the next few slides I'll explain exactly why. So the position of components, for instance, gear, flaps, speedbrake lever, or what have you, can be determined either by switches or by sensors. Now, a switch is something that's got moving parts, those moving parts, they physically reroute the path that the electricity can take. An example of that is the speedbrake arm switch. Proximity, I'll say this one last time, I hope, proximity switches or sensors have no moving parts and are therefore more robust than switches. This allows them to be used in harsh environments such as the landing gear, doors, or the tailskid. And that right there, if you read it closely, it says on it, right air ground, indicating sensor. So it is a sensor, it is not a switch. Now, a proximity sensor, it's actuated by the nearness of a ferrous target. So the two states of a proximity sensor are near or far, whereas on a switch it's open or closed. Very sort of binary. But near or far, it's actually a range. So the near or far actually corresponds to a voltage generated by the sensor. That voltage is processed by a remote unit, which is the PSEU, where the actual switching occurs via solid state transistors. So again, the switching, the switches, if you like, are in the PSEU. The bits that tell the switches whether to open or close are the sensors, and they're actually out there on the gear or in the tailskid or on the flaps in the the high stress environment. Now, when proximity sensor technology was developed, it was a reliability improvement compared to mechanically actuated switches. However, proximity sensor technology requires a remote processing unit, hence the need to bring in the PSEU. The FSEU, the Flaps Electronic Unit, is similar. It's the same sort of thing in that it serves as the remote processing unit for the numerous proximity sensors that are on the wing leading edge. So that's what they are. And on the picture here on the right hand side, you can see that this is from the MaxM data pages. You can see that the state of the various places where there are sensors is either being recorded as near or far. So let's put this all together. Photos show you got the sensors on the landing gear. They feed into the PSEU, and you can read the PSEU output on the Max data Max pages. So in this example, which again I've only shown it on the Max, so because you can see the outputs of these, but the same thing happens on the NG. You just can't see it as well. This example's on the right main landing gear. There are two air-ground sensors that measure the compression gap. Notice, and I think you can just about see it on this photo, that those sensors are not actually closed, that there is a gap there. Even though you got the full weight of the aircraft on the wheels there, they don't close. They don't need to, because it's not a switch, and it's better if they don't, because they're sensors. So these signals are then sent to the PSEU and displayed as shown on the maintenance data page of the MDS. So with the example that I've highlighted at the bottom right of the screen in the red box there, so the right gear air ground, you can see that the gaps in mils are 130 and 121 millimeters respectively. And because the range, which is shown in the right hand column there, for a near state is between 0.58 0.58 and 152 mil, the result is near. That means that there's weight on wheels, therefore the aircraft is on the ground. So that's kind of how it works. Now that's hopefully tying together and bringing in sensors right the way through to whether the aircraft's on the ground or not. So talking of air ground, air ground sensing and reporting is the main function of the PSEU. It's not accurate to say that the PSEU is the air ground system. The air ground system contains the PSEUs, and the PSEUs or the air ground systems contain the PSEU, and the PSEU is the major component of it. But the PSEU is nevertheless just one component of the air ground system. So there are 6 air ground sensors on the aircraft. There's 2 on each gear, 2 on each main landing gear and on the nose gear. The sensors and targets, which we've been through on the previous slides, they're on each side of the upper torsion link and the lower outer cylinder. So when the axle compresses the torsion link to meet the outer cylinder, the air ground sensor closes, in inverted comma, the gap reduces and a ground is recorded. The air ground sensors on each landing gear feed into the junction boxes, which you can see there just above the sensors and in the photo, then onto the PSEU, which controls the air ground relays. The air ground status is used by numerous aircraft systems. Yes, it is, and I'll list them very soon. But just continuing this for a moment, there are 2 air ground systems for redundancy. So it isn't just one. They because of the ramifications of knowing where the aircraft's on the ground or in the air, they've split this out into 2 systems. One air ground system from each gear is used in each air ground system for independence. So again, it's all about redundancy, which should be screaming to us how important the air ground systems are. The outputs from the PSEU are 12 air ground relays, numerous, I mean dozens, of air ground discretes, and the PSEU light in the flight deck. The relays themselves, they're actually located in two hermetically sealed junction boxes, which are accessed from either side of the nose wheel well. So again, next time you do your walk around, pop your head up into the nose wheel well, and you will see these hermetically sealed junction boxes, or you will see the front plate on them. That's one with the nose gear extension decal on it, which has nothing to do with what's behind that panel, but it was a good place to put that decal. So, air ground overview. The sensors and switches, again, weight on wheels, gear up locks, alarm locks, pivot lever, doors, airstairs, blah blah blah, and the flaps as well from the FSEU, all feed into the PSEU. The systems controlled by the PSEU I've already listed before, but of those, the air-ground relays and discretes, they feed into the following systems. So the systems which use air-ground are, and again, this is not an exhaustive list, but things like the flight control computer, the GCU, load shedding functions, APU, TCAS, flaps flight electronic unit, thrust reversers, EC, heaters, all kinds of heaters like drain masters, amongst other things. The overflow overboard exhaust valve, nitrogen generation system, predictive wind shear, nose wheel steering, CVR, the SMID and the SCEU on the Max. Full list to follow, I've said. You will get the full list. But let's go through a few of those that I've just listed in a bit more detail. You probably worked out most of them yourself as I read them out, but just to spell out, for perhaps the new guys coming onto the aircraft, what they do. So there are two FCCs, as we know. They are flip-flopped, master-slave each flight. That has to be done by knowing whether the aircraft's taken off and landed, i.e. constituted a flight. That will flip-flop the master FCC. To reset the GCU to automatically close. Load shedding logic, which is different in flight to on the ground. A subtle one, the next one, the APU-SCU has got a control function to prevent the DC converter from depleting the battery below limit. Those limits are different on the ground and in the air during DC start attempts, so you don't drain your battery. For TCAS to prevent mode Alpha and Charlie replies on the ground. For the FSCU to reset a trailing edge skew or asymmetry. To inhibit thrust reverser in flight, so we can't accidentally select that, or it can't accidentally select itself. For the EC to switch between ground and flight idle. To enable heat for the door area, drain mass, pitot and probes. Overboard exhaust valve logic control. Switching the nitrogen generation system on or off. Again, that's only on flight. To enable the weather radar, PWS takeoff or approach modes. To disable nose wheel steering in flight, and to enable CVR racing on the ground only. So that gives you a flavour, and again, this list is also not exclusive, but it gives you a flavour for how far-reaching the air-ground systems are, and hence the need why we've got two of them. Another thing perhaps to mention is the use of discrete. So an air-ground signal known as a discrete, so it's not a relay, it's not flicking a switch or switching something on and off. It's just reporting whether it's air or ground. That's what's known as a discrete. It's used by many systems that don't need air-ground information to behave differently, as all the ones on the previous slide did. These systems use the air-ground discrete to set the flight leg count in their internal memory, or for fault recording as either an airborne or a ground fault, and also to inhibit test functions in the air. These systems include avionics such as FIRWIRE, DME, ADF, multimode receivers, TCAS, GPWS, the FMC, and the RADALT. So again, all of those you use discrete, and again, that's also not an exhaustive list. All right, here it is. That the long-awaited promised full list. So, as I say, there are two air-ground systems for redundancy, and I'm not going to read them out, but they're this is basically pulled from the maintenance manual as being all the systems which use air-ground information. So it is quite a lot. Now, many systems are only active when in the air, or certainly behave differently when in the air. And engineers sometimes need to troubleshoot or test these systems in their in-air mode. So to do that, they have to fool the aircraft into thinking it's in flight. Now, every generation of the 737 has got a different way of doing this through its PSEU or equivalent older units. So, on the originals, you did it by pressing both of those S1 and S2 sensing buttons. On the classics, it was similar. There was an air and ground sensing button there down the bottom left of the of that E11 shelf. On the NGs, you do it via the bike panel on the PSEU. And on the Max, most civilized of all, you do it from the comfort of the flight deck using the air-ground override. Now, hopefully, they're not applicable to pilots, but certainly to engineers. There have been numerous cases over the years of aircraft collapsing, or as the gears being retracted, or leading edge devices suddenly extending because the aircraft thought it was in flight, and as the airspeed was low, thought it was stalling, so the autoslats deployed. The landing gear transfer unit may kick in because obviously one of the engines is not running. All the heaters will start to operate if they're switched on, or the automatic systems, NGS as well. So there's a whole lot of things which will start to happen quite quickly if you suddenly tell the aircraft it's in the air. So follow the steps in the airmen very carefully. Take the appropriate safety measures before putting the aircraft into air mode, I guess, is the takeaway from that. All right, so other systems, that's air-ground sort of done to death. The Airstairs. So the airstair controller warning, which gives you indication about the state of the forward airstair door and turns on the airstairs light when the forward airstair is not closed and locked. This all comes from the PSEU. The door control relays are actually in the J23 box in the E&E bay, same box as where the SPSEU is fitted. Which actually, the more I think about it, the more I think that's less of a coincidence. But anyway, door warnings and flight locks. This is probably what we as flight crew best know the PSEU for. They're all triggered by sensors in the door locks. Circuits for the door warning lights are in the PSEU or the SPSEU for the mid-exit doors. If a door is unlatched, the sensor will detect it, signal the PSEU, and the PSEU will then illuminate the corresponding door warning light. Flight locks. Bit more tricky, these things. The overwing exit and mid-exit doors, we know, have got flight locks. They activate on the takeoff roll, high thrust levers above 53 degrees, to prevent them being opened in flight by the passengers. The flight locks are solenoid held plungers which hold the door lock shaft into the lock position. Those solenoid held plungers are controlled by the PSEU for the overwing exits and the SPSEU for the mid-exit doors. They're DC powered to the locked position, so if DC power is lost, the locks will release. A tension spring also pulls the flight lock pull to the unlocked position. If a flight lock fails to engage when the thrust levers are advanced for takeoff, the associated door light will illuminate. I'm sure we've all seen this in our 737 careers more than once. If a flight lock has failed locked or a fault is detected, the PSEU or SPSEU light illuminates but will be inhibited in flight. The landing gear transfer unit, or landing gear transfer valve as the engineers refer to it. The normal source of hydraulic power for extension and retraction is the A system. But if engine 1 is lost, retraction of the landing gear would be slow because it'd be just using the electric pump only, because your engine-driven pump has gone with the engine, obviously. That will compromise engine out climb performance and invalidate your takeoff performance. So a solenoid-held valve, the landing gear transfer valve, is automatically energized by the PSEU, or your equivalent on the classics and originals, to use System B engine-driven pump for retraction only. If you're airborne and engine number 1 M1 is less than 50% and the gear lever is moved up. So the photo there, that actually is the landing gear transfer unit. You can see it in the wheel well on the keel beam, between the two wheels, forward wall, and there is a white wiring loom going in there on the right hand side. That is what is coming from the PSEU. Takeoff and landing config warnings. So the criteria which I won't go over again. They're all in the FCOMs. When thrust levers are advanced beyond 53 degrees, if any of those conditions are met, the takeoff config lights will illuminate and the intermittent horn or a warning will sound. All controlled from the PSEU. Perhaps less well known is that the takeoff config warning can occur after takeoff if the ground spoiler interlock valve on the NG or the control module valve on the MAX remains open when the flaps are retracted after takeoff, which is quite alarming if it happens to you. Landing config warning criteria again in the FCOM. Any of those conditions are met, the continuous horn will sound, and that's all controlled from the PSEU. Gear position indicating and warning. So there are 2 uplock and 2 downlock sensors on every gear. So again, these are not the weight on wheels ones that we saw earlier, down just above the wheels. These are up near the top of the landing gear. You go into the wheel well, you can see them. They're labelled, but just look for any sort of wires going into things, and they will undoubtedly lead you to these sensors. So there's 12 of those in total. They each send a signal to the PSEU which processes them and controls the gear indicators. For what it's worth, System 1 controls the main indicators and System 2 controls the auxiliary indicators. Just remember, green lights tell you that the gear is down and locked. That's all you need to see. The red lights are telling you something subtly different, just that the landing gear is in disagreement with the gear lever position. But take it from me and Boeing, if you've got green lights, you're okay, you're safe. The gear is down and locked. Almost doesn't matter what the red lights are doing. With the gear up and unlock the gear lever and the lever up and off, all lights should of course be extinguished. Speedbrake deployed, indication and warning. So on the NG, the PSEU controls this the Speedbrake's extended light. On the MAX, it's controlled by the spoiler control electronics unit, but the logic's exactly the same. It'll illuminate if it detects either an unsafe condition or a failure condition. The unsafe condition is that if the Speedbrake lever is extended beyond 7.5 degrees, and you would think it was if it's extended at all, but that just allows a little bit of leeway between where you're trying to arm it and where you're trying to use it. So if the Speedbrake lever is extended beyond 7.5 degrees, i.e. more than arming it, with the flaps greater than 10 in flight but below 800 rad-alt. The failure condition is if the aircraft's on the ground and the ground spoiler actuators receive hydraulic power with the Speedbrake lever in the down position. So that's the failure mode. Two-position tailskid. So the SFPs have got these, and the 900s, all the long body aircraft have got these. This will extend 5 inches for landing, and it gives higher angles of attack on landing with a corresponding reduction in approach speed and landing distance. So that's what this is all about. The SPSEU tailskid card, remember that's the one in slot A on the right hand side, that controls a relay that provides a 28 volt DC bus 1 power to the solenoid control valve in the tailskid actuator. That allows hydraulic system A to extend or retract the tailskid as required. It'll automatically extend the tailskid when the aircraft's in the air for more than 2 minutes and the gear is extended. So in other words, not takeoff, i.e. landing. It retracts it again when the aircraft's been on the ground for more than 5 seconds, or the gear lever is not down, i.e. a go around, or both engines are not running, shut down, or oddly enough, in a glide. Crew procedures. So we've mentioned the lights before, but let's just talk about what happens if you see a light. So they're all inhibited on the takeoff roll when the thrust lever angle's beyond 53 degrees and in flight until 30 seconds after landing. So you should never see these come on in those circumstances. If you do, you've got a very strange fault going on, which is worth writing up in the tech log. If the PSEU light illuminates and does not extinguish when master caution is reset, then you've got what's called a non-dispatchable fault. QRH says don't take off, and in this condition the PSEU light can only be extinguished by fixing the fault, i.e. get the engineers on the case. However, if the PSEU light will extinguish when the master caution is reset, or you only get the PSEU light on recall, then you've got a dispatchable fault which you can go with. My usual caveats: follow your own company guidance and advice, and on this, don't just turn around to your flight ops team and say, "Oh, Chris said you could." This, as I say, is just a generic way of operating. The PSEU QRH procedure, it varies depending upon the type of fault and also the PSEU update version. I'll mention the update versions in a moment. If it illuminates for aircraft with update 4 PSEU, and there should be none of these on the line anymore, all of the faults were non-dispatchable and you couldn't take off. Since update 4, it can now extinguish with a master caution reset, and that gives you a dispatchable fault and takeoff is permitted. If it doesn't extinguish, then the QRH will invite you to try setting the parking brake or shutting the engines down to reset the system. I said these steps came in 2006 with the -5 PSEU. If the light then extinguishes, then a takeoff is permitted. If it doesn't, it's a no-go. Back to stand, call the engineers. On the with the SPSEU light and the maintenance light, it's all far more straightforward. If it illuminates, don't take off. End of story. These lights will not extinguish with a master caution reset, and they're non-dispatchable faults. Problems and updates. I've already mentioned the updating of the PSEU. It's had many updates since it entered service, most of which were during the early years of the system while they were ironing out the initial teething troubles and wrinkles. The -1 was was just used on the prototypes. The -2 was the first in-service PSEU, came in obviously right at the back end of 1997. The -3 came in a few years later in 2000, then the -4 in 2001. That was made mandatory by AD 2004-0710, which I think I mentioned in a couple of slides. The 4A was introduced in November 2005, which had SIP pin improvements, and the 5 came in 06. With improvements to dispatchable fault condition indication logic and false door warnings. And the last update was the -6, came in 2012, and had improvements to things like the stab trim, disagreed landing gear transfer unit, and the rad-alt fault conditions. So there hasn't been a later PSEU than the Dash 6, other than of course the Max one, which was a whole new PSEU. Here we go, AD 2004-07-10. So this basically mandates that any old PSEU, a Dash 2 or 3 in service, remember the Dash 1 was only on the prototype, so never made the line, be updated to a Dash 4 standard. And this was because a nuisance or a gear warning could occur after flap retraction that couldn't be silenced other than by pulling the aural warning circuit breaker. Boeing introduced an FCOM bulletin about it, warning us not to pull the aural warning circuit breaker because it'll disable all other aural warnings. So the unintended consequences of doing that could be actually quite dire. This led to a temporary change in the QRH procedure, which effectively prohibited the dispatchable faults on the PSEU. Nuisance faults. So the PSEU, like all other systems that are reliant on proximity switches and logic, has been prone to various nuisance faults. One obscure example I read about was on the Dash 5 PSEU, where it was normal for certain LGTU power faults to be logged in the byte fault history. So they weren't current faults; these were transient faults or faults which had occurred for a while and then would miraculously clear themselves, and nobody could ever catch the aircraft with one of these faults current. A lot of troubleshooting went on, or detective work, and it was found that these faults occurred when the cabin was being serviced with the aircraft doors closed. And this was due to the electrical power source, which was DC bus 1 to the LGTU, not being powered when the PSEU was powered. And it only happened when the ground service bus was powered with external power connected. So it had to be this obscure combination of the ground service bus powered with external power and the cabin doors being closed. Then the LGTU would register this fault. Anyway, Boeing issued a maintenance tip bulletin on it stating that if these faults were found in history, then they could be considered nuisance and ignored if it's confirmed that they're not present as an existing fault. And that was one of several issues that were addressed in the Update 6 PSEU. Nuisance warnings, these are the ones we're all familiar with. The big common one was when thrust levers were set for takeoff, the takeoff config warning horn would sound because the Speedbrake was not fully seated in the down detent. So you could either just give it a bang, or hopefully double check, give it a bang at the gate, during your cockpit prep checks, make sure it's there. Boeing issued this flight ops technical bulletin advising crew to push the Speedbrake lever firmly down to ensure it's in the down detent. Operator reports of rejected takeoffs and takeoff warnings linked to this decreased significantly following the release of this bulletin. PSEU Model 5, Boeing actually changed the takeoff warning switch input from the Speedbrake, not downside the switch to improve the reliability of the signal, indicating that the Speedbrake isn't stowed. So again, these things all gradually get ironed out with time. And the other one is, of course, the overwing exit door lights coming on when you set takeoff thrust. In 2006, again, PSEU Model 5 came to the rescue, changing the logic from only needing one system to say the flight lock had failed to latch to needing both systems. That did significantly reduce the number of false door warnings on takeoff and PSU-related RTOs, but they do sometimes still occur, as we know. But a lot less than they used to occur, so it is progress. That's it. That's the PSEU, the revamped version of the video. If you've enjoyed it, give it a like, subscribe to my channel, and if you want to support the cause, consider buying a copy of the book. Thanks very much for listening.